Okay, so the next thing to be able to do in polar coordinates is to be able to graph an equation in polar coordinates. Let's think about what the graph of a function looks like in Cartesian and rectangular coordinates. And I've Cartesian or rectangular; they mean the same thing. I've written them. I've written that on the left here. You've seen me draw this graph many times. This is just sort of my generic drawing of what a function looks like. So this is the function y equals f of x. But if you think about what this means is I like to think of functions in terms of input and output. So basically, what the function is telling you is it's saying, give me some horizontal position and I'll give you a height. Or you could say, give me the number of steps that you walk to the right and I'll tell you how many steps you should walk up. That's really what y equals f of x means. So here, what I have is I have the point x comma f of x. Don't know why I didn't put that parentheses in there. And what it's saying is, if I've walked a distance x to the right, which I've written like that, then it's telling me that I need to then walk I need to walk a distance f of x uh, up from the x-axis in order to get to that point. So for polar coordinates, we have kind of a different sense of what a function means. We write a function as r equals f of theta. So typically theta is the independent variable, and what we're saying is, give me an angle that you would like to turn around the center point, and I'll tell you then how far to walk in the direction of that angle. So what I've drawn here is sort of the equivalent of my typical function that I usually draw in rectangular coordinates, where it's kind of wavy, but it's still a function. It still passes the vertical line test. What I've drawn here, this kind of blob, is what a typical function looks like in polar coordinates. And perhaps you would guess that the issue is that since I have to have a unique radius for every angle input, instead of a vertical line test, what there is kind of a radial line test. In other words, as I draw a radial line out from the center outward, I can only intersect one point on the curve. If that's the case, then I've in fact found r as a function of theta. So the sense of what's going on here is that if we pick an arbitrary angle theta, which I've drawn here in red like that, um, the function should tell me how far away from the origin I should be. So this point that you see here, this purple point, is it's the point f of theta comma theta. It's a little confusing because we put the independent variable second instead of first like we usually do in rectangular coordinates, but that's just the way it goes. So the idea is I get to pick what angle I'm going to turn around the origin, but the function is going to tell me how far to walk in that direction in order to get the point. And so this point, the purple point, was generated in that way for some arbitrary function f. I haven't really indicated what that function looks like. Um, here's an example. This is a fairly simple example of a function that we can graph. Let's just graph the function r equals theta on the interval 0 to 2 pi. So let's put up a piece of polar graph paper right here, and I'm actually gonna draw in the concentric circles. So that's circle of radius 1. Actually, I'm going to call each of these, we're going to call each of these 2 units. It'll just be a little bit more convenient. So I'm going to call this radius 2, this is radius 4, and this is radius 6. Okay, so let's just think about what some values would look like. So let's put up a table. Theta is the independent variable, so let's put in theta, pi over 4, pi over 2, 3 pi over 4, and pi. So, all right. So since r equals theta, this is going to be when theta equals 0, r equals 0. When theta equals pi over 4, then r equals pi over 4. Just to get some scale, I'm going to convert this to decimal. We don't really emphasize decimal conversions, but just to give you some idea of where we are, this is going to be approximately 0.8. And pi over 2, that's, of course, the exact value of r is going to be pi over 2, but that's going to be approximately 1.6. At 3 pi over 4, that's going to be approximately 2.4. And then pi, of course, we know is, the exact value of r is going to be pi, but its approximate value is 3.1. Okay. And normally we don't deal in decimal approximations, but we're trying to graph this, so I just thought it would be useful to write these approximate values. So at a radius of, doing this color, at a radius of pi over 4, actually, let's graph the 0 first. So one point on this graph is going to be the point 0, 0. Recall that it doesn't really matter what the angle is if the radius is 0 because we're just looking at that point there. Okay, so at pi over 4, I've put in this radial line which is at an angle of pi over 4. I want to go a distance of zero point 0.8 from the origin. So that's going to take me to about here. And then at an angle of pi over 2, that's just going to be the positive y-axis. At an angle of pi over 2, I'm going to go a distance of about 1.6. So that's going to take me to about there. And then at 3 pi over 4, I'm going to be a distance of 2 pi over 4. So let's see. Here's the line. That's the angle 3 pi over 4. And I want to be 2.4 units away from the origin. So since each of these concentric circles represents 2 units, I'm going to go a little bit beyond the first circle to there. And then finally at pi, which is just going to be the negative x-axis, that's an angle of pi, I'm going to go 3.1 units from the origin, which is right about there. So let's start to draw what we have. We have kind of like, it's looking a little bit shell-like, maybe a little spiral-like. Let's see what we continue to get. I don't have to put in all of these points, but let's put in 3 pi over 2. So 3 pi over 2 is about 4.7. So the exact value of r is 3 pi over 2, but I'm going to write this as approximately 4.7. So that takes me to, the second concentric circle is 4, so I want to go about 0.7 beyond that. That takes me there. And then finally, let's do 2 pi. I don't know why that came out in that color. 2 pi, which is, r is going to be 2 pi, which is approximately 6.3. That takes me, the third concentric circle is going to be 6 because each of these is 2 units, and that takes me about there. So looks like that's my shape. So this is the graph of r equals theta. It's kind of interesting to note that the equivalent, like y equals x, would look like this. The graph of y equals x looks like that. But this is the graph of r equals theta. So polar coordinates really is a very, very different shape system from rectangular coordinates. This very simple line y equals x looks like, it's just a pure diagonal line. In Cartesian coordinates, we do the equivalent thing, r equals theta, and we get this spirally looking thing in polar coordinates. That's just the way things work out. But this is the sort of the mechanics of how you would graph something in polar coordinates.